Have you ever questioned how smart you truly are? How about why are some people smarter than others? Or maybe you've met someone with a far better memory than you. These are just some of the questions facing researchers when defining intelligence. So, what is intelligence? Throughout the test of time, definitions of intelligence have circulated. The American Psychological Association describes intelligence as individuals differ in the ability to understand complex ideas, to adapt effectively to the environment, to learn from experience, to engage in various forms of reasoning, and to overcome obstacles by partaking in problem solving. Alternatively, first proposed by Professor Linda Gottfredson, she defined intelligence as a very general mental capability. It is not merely book learning, a narrow academic skill, or test taking smarts. Rather, it reflects a broader and deeper capability for comprehending our surroundings, catching on, making sense of things, or figuring out what to do. No matter how intelligence is described, it is widely accepted by neuroscientists that the common factor to all definitions is general ability. All definitions of intelligence have the same inherent challenge for neuroscientists. How do you measure intelligence for empirical research? Firstly, key terminologies must be clarified. Using this diagram, here we have many mental abilities, anything you can think of from multiplying in your head to picking stocks. The large circle is representative of all mental abilities. Intelligence refers to the mental abilities directly relating to your everyday tasks. G or G factor is your general intelligence, and IQ is a test score based on your performance of a subset of mental abilities that relate directly to your everyday intelligence. The IQ circle encompasses a large portion of your intelligence because IQ is a good predictor of your G factor, which is the basis to all neuroscience testing. Importantly, different mental abilities are not independent. They all relate to each other, and the correlation among mental tests are always positive, meaning if you do well in one kind of test, you tend to do well in others. This is the core finding of intelligence, and the relationship among mental tests is called the structure of mental abilities. To picture this, imagine a three-level pyramid. At the bottom row, we have many different IQ tests of specific mental abilities. In this illustration, there are 16. At the next level up, similar abilities are grouped into more specific factors such as reasoning and memory capacity. For example, tests 1, 2, and 3 are all reasoning tests. Ultimately, this common factor of intelligence is called the general factor of intelligence, or G, sitting highest on the pyramid. This G factor is the basis of all IQ testing, which is normally distributed and follows a bell-shaped curve. The average IQ score ranges from 85 to 115, which captures 68% of the population. Below a score of 85 is considered low intelligence, and beyond IQ of 155 is considered high intelligence. Beyond a score of 130 would mean that you are among the top 2% of the population in intelligence. Your IQ performance is dependent on your activity of the parietal frontal regions of the brain. Where in the brain is intelligence? Thanks to the dawn of neuroimaging, the current leading theory of intelligences in the brain is parietal frontal integration theory, or PFIT, which associates the connections of the neurons in and between the frontal and parietal lobes to be linked to an individual's difference in intelligence. This theory proposes that intelligence is processed through a four-stage response corresponding to specific Brodmann's areas, which are isolated localizations of brain function. Stage 1 involves areas 18, 19, 37, and 22. It is responsible for processing sensory information, with visual stimuli activating extrastriate cortex and fusiform gyrus, coupled with auditory information activating Wernicke's area. This information is sent to the parietal cortex for stage 2, concerning areas 40, 7, and 39, known as the supramarginal, superior parietal, and angular gyri respectively, where it is prepared for integration. In stage 3 of areas 6, 9, 32, 10, 46, and 47 moves information into the frontal cortex, where it collectively interacts together for evaluation and hypothesis testing. Once a solution has been identified, stage 4 sees the activation of the anterior cingulate of area 32 to inhibit other response regions. Additional imaging studies with this theory have shown that a well-developed gray matter of area 40, which is the right inferior parietal, assists with the processing of information. White matter of the arcuate fasciculus, Jesuin's area, and frontal parietal occipital regions increases the efficiency of information transfer across different brain regions during integration. Finally, bilateral cortical thickening in areas 10, 11, 47, 36, 7, and 40 indicates an individual influence on intelligence. As we can gather from PFIT, intelligence is not necessarily isolated to a specific region in the brain, but in fact requires the activation of numerous areas in combination. These areas activate and deactivate based on different environmental and biological influences, which can affect an individual's response to given situations. Environmental factors generally consist of previous experiences, type of education, and lifestyle choices. These areas can be improved upon based on the quality of information they are exposed to. However, biological factor limits individuals' ability to develop upon their intelligence and are generally governed by factors such as gender, mood, disease, and genes.
The future direction of intelligence seems promising and opens a scientific frontier to developing wide-reaching impacts, ranging from possibly boosting intelligence for society, greater psychometric screening, to curing memory disease. Here are some of those new insights. Chronometrics is an emerging method of measuring information processing speed while performing standard cognitive tests, one that can provide a quantitative measure of intelligence on a ratio scale. Longitudinal studies of twins reveal insights of having the same G factor, regardless of having environmental factors, prompting future genetics research into proteome gene expression in neurons within those parietal frontal regions. There's a skewed variance in intelligence between genders, and is still grey, requiring future research. New neuroscience techniques such as optogenics, chemogenetics, and neuroimaging studies of consciousness and creativity can help provide insights into delaying the onset and progression of Alzheimer's.
With the complex nature of intelligence, neuroscience progress offers a positive outlook to society and exciting opportunities to possibly broadening the horizons in both medicine and psychology.
Intelligence. It is more than just a test score.